Thank you. Numbers play a terribly important part in our lives, and in fact, we might not think this is the case, but for example, you wake up because it says 6:45 on the dial, although actually if you're a professor, it's more like maybe 8:15, depends whether you have a class or not. And I would know that if it was the 10th day of the month when I lived in Halifax, Nova Scotia, then the Royal Bank of Canada would take $10.50 out of my checking account, and of course my checking account had a number. But as the morning progresses, I might put on channel 355, which is CNBC, which is a news channel devoted entirely to numbers, and they might tell us that the Dow went down by 220 points, or the NASDAQ went down by 320 points, or that we're trading at 110 yen to the dollar, or 67 American cents to the Canadian dollar. We might get a weather forecast, and that would be in degrees Fahrenheit. We actually have degrees Fahrenheit in Dallas. We have positive temperatures there. Yes, I know. And as I travel to work, I might travel down Interstate 75. Somebody might call me. They would use a telephone number. My house is a number to actually remind me where to go in the evening, and so forth. And so we have all these numbers swirling around us, and so the question beckons as to whether there are patterns to the numbers that we see in everyday life. And indeed, numbers go back many years, and I do believe that numbers have contributed as much to our well-being as has the wheel, fire, and agriculture. If we took numbers out of the American economy or the American society as we know it, we would actually cease to function. If you think about it, for the past 5.5 weeks, we've had a little trouble with numbers down in Florida. And of course, it was a case of whose number was biggest. When I was in high school, it was who had the biggest muscles, and that person was kind of president. And so in this case, a little more civilized, it's who had the biggest number. So we have all these numbers, and the question beckons as to whether there are patterns to the numbers that we see in everyday life. And so I think it's only appropriate that we start off with a reading from the book of Numbers, chapter 1, verse 26. And the Israelites were in the desert, and they were told to take a census. It says, all the men 20 years old or more who were able to serve in the army were listed one by one according to the records of their clans and families, and the number from the tribe of Reuben was 46,500. This is, of course, the oldest list of numbers that I could find, and it goes back some 3,000 years. So I ask you at this very early hour of the morning, what patterns do you see in the list of numbers? All 5 digits, thank you. Okay, end with zeros.
They're all sort of clustered around the middle, right? It's like 3, 4, 5.
Clustered around the middle, but you're not supposed to be looking at digits yet. We'll defer that. The point I do want to make is that when we have a list of numbers, and the list of numbers is short, and the patterns to the digits in the list of numbers is reasonably blatant, we can see it with a human eye. When I give talks to auditors, we're not really confronted with a list of 12 numbers that's short with blatant patterns. We're confronted with a list of numbers that could be up to 100 million in a database. So we might come back to this before we finish, because there was a second census. And so we have to move ahead. Somewhere here.
Slide number 3.
Press pause. We have to move ahead to the 1930s to Frank Benford, who was a physicist at the GE Research Laboratories in Schenectady, New York. And he discovered that the first few pages of his logarithm table books were more worn than the later few pages. From this, he brilliantly deduced that he was using the first few pages more than the last few pages. Now, the first few pages had a little trick to them. The first few pages give us the logs of numbers with low first digits. So just so that we understand what the first digit of a number is, the first digit is always the leftmost digit. And so my flight into Boston yesterday, which was not in my original flight plan, but nevertheless it was flight 198, And so if 198 were a real number and not simply a label that we put onto a flight, then the 1 would be the first digit, the 9 would be the second digit, and the 8 would be the third digit. 0 can never be a first digit, even though from time to time we do need to write a 0 in the number to actually tell us what the number is, as in 0.08. You need the 0 there, but it can never be the first digit. So, the logs of low first digits are at the front of the book. The front of his book is more worn than the back of the book, and from this he hypothesizes that maybe he's looking up the logs of numbers with low first digits more than the logs of numbers with high first digits, perhaps because in the world there are more numbers with low first digits than with high first digits. That's why he uses the front of the book more than the back of the book. Well, he set out on a crusade, and I spent some time talking with the historians, the GE corporate historians in Schenectady, and they said that around about the late 20s and the early 30s, we had this Great Depression, and the staff were mainly on half days. So he had the other half of the day to do something with it, and apparently he spent it looking at digits. And he then went and he analyzed 20 lists of numbers with a total of 20,229 observations. And you can imagine at that stage how much work that would have been. Everything would have had to have been done by hand. And sometimes I think that he would get tears in his eyes if he actually saw us doing 20,000 numbers in Microsoft Excel with the software in perhaps a matter of 2 or 3 minutes when the computer works. So he analyzed these 20 lists of numbers, 20,000 observations, and these were very diverse lists of numbers. One of them was, for example, all the numbers in an issue of Reader's Digest. Another one was populations. Fourth list was the drainage areas of rivers. Others were scientific constants. One list, which did particularly well, were all the numbers from stories on the front pages of newspapers for 100 consecutive days, of course excluding the dates and the price, because the price probably didn't change much then. And so he had very diverse lists, and lo and behold, at the end of the day, when he averaged his results, he did find out that 31% of the numbers started with a 1. 18% of the numbers started with a 2. And if you add those two percentages together, we get 49% of the numbers starting with a 1 or a 2. So we can do some complex arithmetic here, and that would tell you that there are 51% of the numbers for all the other 7 possible first digits. So the 1 and the 2 flat out absolutely dominate lists of numbers. So this was his sort of empirical test, 6 years. We can actually do a whole PhD in faster than 6 years. And then he set out and he started making some assumptions, and he formulated what we have now come to know and love and call Benford's law, and it looks like this. It's slide 4. There it is. And so what this tells us is that as a first digit, I expect the digit 1 to be a first digit 30.1% of the time. I expect the 2 to be a first digit 17.6% of the time. I expect the 3 to be the first digit 12.5% of the time, and so on and so forth until we get down to the 9. Expected as a first digit 4.6% of the time. In the second position, the 9 in 198, I expect 12% of the numbers to have a second digit 0. And then again, we have decreasing frequencies down to 8.5% for the second digit 9. You can see that as we get to the third digit and the fourth digit, the probabilities smooth out so that the digits now become almost equally likely, but there is still a bias towards the low digits. The low digits are the dominant digits. So usually at this stage, when I'm talking to auditors, I say, you know, we can go one of 2 routes. I can show you the integral calculus, and that will take all day. And then at the end of the day, I can summarize and tell you that how we might possibly be able to use it in auditing. That would be my sort of concluding few sentences. Or I can give you an intuitive explanation. And if you like the intuitive explanation with some examples, we can carry on with our lives. Usually they take the intuitive explanation. I'm a little nervous of making the same offer to this audience this morning, but nevertheless, I'll ask you, which would you like? The calculus or the intuitive explanation?
Both.
I heard intuitive, so... Yes. So this is the intuitive explanation. If we think of the Dow Jones Industrial Average at 1,000 points, was it 1,000 points of Dow? Was that somebody, George Bush? Wasn't quite 1,000 points of Dow, but at 1,000 points, the Dow has got a first digit, 1. It keeps that first digit 1 right until the split second before the Dow gets to 2,000. And so what percentage increase do we need to go from 1,000 to 2,000? 100%? If the Dow is going up at 20% per year, just ignore compounding, 5 years with a first digit 1. At 5,000, the Dow has got a first digit 5. It keeps that first digit until the split second before we reach 6,000, and we only need a 20% increase to go from 5,000 to 6,000. So if the Dow is going up at 20% per year, we've got 1 year with a first digit 5. At 9,000, we have a first digit 9. We keep it all the way up until 10,000, and we only need an 11% increase to go from 9,000 to 10,000. Again, once we reach 10,000, we have a first digit 1, and again now we need the 100% increase to get through the 1s. And at 50,000, we'll only need a 20% increase to get through the 5s. So this pattern would repeat itself for the Dow. Because you need that 100% increase to get through your 1s, you're going to have a first digit 1 for far longer than any other first digit. The same would apply to, for example, the populations of cities. Many years ago, Los Angeles would have had a population of 100,000 people, most of them actors. But again, it would have needed a 100% increase to go from 100,000 to 200,000. You always need that 100% increase. The same would apply to the total assets of mutual funds. They would need a 100% increase in assets to go from 100 million to 200 million. The total market capitalizations of corporations, you need a 100% increase in your market cap to go from 1 billion to 2 billion. So you always take much longer to get through your 1s than you do to get through your 9s. And if you really do the DDXs and the calculus based on that, you will come up with Benford's law as it stands. Would Benford's law apply to every single list of numbers in the world? No, not at all. In fact, it just applies to very many of them. And in fact, it would apply to even more if we took all the list of numbers that we had and just threw them in a bucket and made sort of number soup. As a kid, I used to enjoy digit soup far more than alphabet soup because it spoke to me. And the few rules that I've discovered that make Benford's law work well are, and we'll talk a little more about Benford's law, is that our list of numbers should be describing the size of some phenomenon. I do want larger numbers to mean bigger things and smaller numbers to mean smaller things. This is not so the case with, for example, airline numbers. Flight numbers, the big flight numbers are not really the long flights, and short flight numbers are not the short flights. Actually, it's the opposite. I also like no built-in maximum or minimum. If my list of numbers has got some built-in maximum or minimum, then Benford's law would fall on its face. And for example, one example of a maximum would be on tax returns we have IRA contributions limited to $2,000. I gave a talk in London last month, and I had to just be clear to them when I spoke about contributing to the IRA that I meant individual retirement accounts. Else there would be problems. But you know what I mean, individual retirement accounts capped at 2,000. And so if I listed everybody's contributions towards IRAs, we'd have lots of first-digit 2s for 2,000, lots of first-digit 1s for people from 1,000 to 2,000, and probably not much else. So that ceiling of 2,000 would cause Benford to not work. An example of a minimum would be, for example, many years ago, my stockbroker had a minimum charge of $50 per transaction. I think he wishes those days would come back, but they're not. I've seen those adverts for Ameritrade, Stewart, and I think it was $7.95 a trade. But for example, if we listed all his commission charges for the month, we'd have lots of $50 for the minimum commission charges coming through, and that would give us lots of first-digit fives, and Benford's law flat out wouldn't work. The third category of numbers, at least my third criteria, which follows from the first two, is that my numbers should not be what I call assigned numbers. And an assigned number is a number that we've given to something in place of words. We do this all the time. Social security numbers, car license plate numbers, checking account numbers, zip codes. We tend to use these numbers as labels in place of words. And those patterns could have, at least those numbers, could have flat out any digit pattern that they like. So those would be my main criteria. I like my numbers to be describing size, no built-in maximum or minimum, and definitely not a list of what I would call assigned numbers or numbers used as labels. Yes, I'm happy for questions.
The max and min, even if you had that, wouldn't you still expect similar distributions for the non-leading digit?
The question was, if I do have built-in maximum or minimums, or you might as well just say, if my first digits don't conform, then maybe I could simply test whether my second digits conform. And the answer there is just a little bit hazy, and that those second digit probabilities are conditional probabilities, and they assume that the first digits do conform. However, the good news is that if the first digits don't conform perfectly, the second digits are still a reasonable approximation of what should happen. That the first digit distribution would have to be absolutely terrible before those probabilities would move significantly. So from time to time, even if my first digits don't conform, I do look at the later digits for patterns. So a little bit of history. The nice thing about Benford's law is that somebody actually read the paper. And if you think back to many years ago, his paper was published in 1938. The only way to read a journal article in 1938 was with the journal in your hand. And so the only way that a stream of literature would have started to evolve from his paper would have been if people actually read the journal article with the journal in hand and then published more papers on the topic so that the stream of literature would actually start. And the good news was that Benford's paper was followed in the journal by an article dealing with electrons and things that had to do with atomic bombs. This was around about the time of the Second World War. And we are very lucky that some statisticians and physicists actually read the electron article, but Benford's paper, the last page of his paper, was next to the first page of the electron article. And so this was actually Goldsmith and Furry, and they wrote a few papers which they published in Nature in 1946 and 1945. And once it got into Nature, now we had a large enough circulation so that people would pick up on this and actually go back. But before we had computers and references and things like that, there is the chance that Benford's paper would not have been read or not have been remembered, and it would still be hiding in some obscure library with no follow-on literature. Proceedings of the American Philosophical Society. I can check it out. But it was... So, this is what Benford's law assumes. It assumes that if we take a set of data, and he called it natural data, which doesn't really have a very tight definition. If we take a set of data and we rank them from smallest to largest. And so I simply do a sort, data sort, smallest number at the top, largest number at the bottom, and I label my smallest number observation number 1, my largest observation number 1,000. If, for example, I have 1,000 items in my data set, then he assumes that we're going to have this geometric sequence. That is the underlying assumption, and in fact it's from this geometric sequence that we actually get Benford's proportions. And so this is, I shouldn't call it observation number, I should probably call it observation rank. And so we're going from rank 1 to rank 1,000. And this data set starts at 10 and goes up to 100. And so what he's assuming is that we're going to have this geometric sequence, that pattern, and that's what he actually bases the calculus on. So from time to time, accountants do ask me, they say, well, can't we simply test whether the data set is a geometric sequence? And if it is a geometric sequence, then I know it's going to follow Benford's law. Well, this is a necessary condition, but not sufficient, because some data sets, although they have all the attributes, they don't follow Benford's law. And a good example of this would be, for example, the total volume on the New York Stock Exchange each day for a year. If we think about the past year, the volume has generally been from 800 million for a day up into 1.5 billion. So we'd have a first digit 8 for 800 million. Somebody else got confused between these millions and billions, to keep it straight here. 800 million, I'd have a first digit 8, or I'd have a first digit 9 for 900 million and something, or a first digit 1 when we went over a billion. So generally, if I did a graph of New York Stock Exchange volumes, I'd have 8s, 9s, and 1s, and probably nothing else. And of course, what this is, I would have a geometric sequence if I plotted this from smallest to largest, but it wouldn't cover a large enough range. And so when I was at the New York Stock Exchange, they said, no, if you went back to 1792, when we actually opened our doors, and you took all the volumes from 1792 up until now, then you would get something approximating the geometric sequence. For example, I remember it clearly, it was January of the year 1901, and it was in January 1901 that the New York Stock Exchange first topped 2 billion shares. That was a major milestone. 2 million shares for the day. And so you can imagine that prior to January 1901, there would have been many, many years when that volume would have been 1 million and something every single day. So they would have had their volumes. So I do need that geometric sequence to actually span quite a range.
Numbers by counting base 7
And the nice thing is that Benford's law is based on logarithms. The question was, could we change it to base 7 or something like that? Yes.
Rescale.
And Benford's law works with numbers to other bases. You do just have to change the formulas. And I do have a German mathematician working on whether we can't just change numbers to different bases and see whether Benford comes out in the end. So work is being done. We'll have to leave that thought pending until next year. Just a little bit more about the history of Benford's law. In the beginning, people read the articles, but we didn't know whether we should believe it or not. And in fact, if you think about it, way back in the 50s or the 60s, any study of data would have been very, very time-consuming. However, in 1961, the statistician Roger Pinkham came up with the ultimate theorem. And this theorem actually put aside any doubts as to whether there was any other law that should be governing digits. And what he found, or what he proved, was that if we have a set of numbers that follows Benford's law perfectly, and we tend to call that a Benford set, I don't know when that name actually originated or who started it, but if I have a Benford set, which being a set of numbers that follows Benford's law perfectly, and I multiply each number in the Benford set by a constant. So I multiply each number, for example, by 7 or by 3, or I could multiply it by 1.4 or something like that. The new list of numbers would also follow Benford's law perfectly. And his logic in the opening of his paper was something as follows. He said, if there is indeed a law governing the digits of numbers that we find in everyday life, then that law should be what we call scale invariant. If the lengths of the world's rivers follow Benford's law, it shouldn't matter whether we measure those lengths in kilometers or miles or coffee cups. The numbers should follow Benford's law in either scale. And if you think about this rather logically, it would be indeed a sad day if the market capitalizations of companies on the New York Stock Exchange followed Benford's law when we expressed them in US dollars, and if the Financial Times took that same list and printed the market capitalizations of companies and they printed them in euros or pounds, which would merely be all the dollar numbers multiplied by a constant, it would be very strange if the new list, the Financial Times list, didn't follow Benford's law, but our list did. And so what Pinkham proved was that if a set of numbers follows Benford's law, then multiplication by a constant will keep the digit proportions. And of course, it's a little harder for me to explain this to auditors, but I think you can sort of appreciate that if Benford's law is based on this geometric sequence, and I multiply all my numbers by a constant, let's say I multiply them by 2, then I'm still going to have a geometric sequence. It's just going to be higher up, but it'll keep that shape. So that's the simple way. But the good news about that was once he proved that, there were no papers that competed with Benford's law. Nobody came up and said, oh, there's Stevenson's law or Negrini's law or any new law. It was now the law. So I just want to take a poll. I have a bit of time. I budgeted 30 minutes for Benford's law theory. I just take just a little poll. If your house number, your street address, the house number, if your house number starts with a 1 or a 2, would you raise your hand, please? Look at that. 48.6%. Very good. So this is a Benford compliant audience. You may stay. And of course, the amazing thing about this is, and what we found is Benford's law applies, and it applies even to lists of numbers where I didn't expect it to apply. And if you think about house numbers, in numbers of the world, we have cardinal numbers, which are counting numbers, and we have ordinal numbers. Ordinal numbers are basically those numbers when you go into a government department, like I dealt with immigration, and you take that little ticket, and that ticket says 55, and of course you see them saying now serving 18, and that number doesn't move. That little ticket saying 55, that's an ordinal number. It basically says where you are in the queue. And of course your house number is an ordinal number. It actually says where your house is positioned relative to other houses. It has nothing to do with the size of your house, yet it actually works. And I found even stranger things, numbers such as earnings per share numbers. On the NASDAQ, I found earnings per share numbers to follow Benford's law, and I've been most surprised because earnings per share is actually, for each company, it's earnings divided by number of shares. So earnings per share is the quotient of two numbers. And it follows Benford's law. Whereas I would have expected the earnings numbers to follow Benford's law, and I would have expected the number of shares outstanding to follow Benford's law, but not necessarily the division of the one by the other. And on the NASDAQ, I found earnings per share. That might be because only 6 companies on the NASDAQ have earnings, but but it follows Benford's law. So I've been, more often I've been pleasantly surprised than I've been unhappy with the findings.
So it's nothing like the law of large numbers sometimes. That's a very naive, vague question, but I'm just...
No, nothing like the law of large numbers. We have had about 150 published papers on the topic, and in the beginning, I read Benford's law in 1989. I was a PhD student, and it was in a stats book, and it just had a half page on the probabilities of digits, and it was April of 1989. And I thought, wow, this is very interesting. And so I went to the library, and lo and behold, the journal was there, and I copied it, and I went home and I read it twice that night, never dreaming that this would actually be my career. And last month I was in London, in Germany. In October I was in Germany. Before that, Luxembourg. I've been to Bangkok. Last week, Minneapolis. So this week, Hanover. I mean, I travel, and this is basically now my life. And so the irony is, of course, that I've got much more out of Benford's Law than Benford got out of Benford's Law. But there's a very good reason for that, and that is that it is only now, with auditing and with computing, that we can actually take a data set of 50,000 numbers or 1 million numbers and do the analysis very cost effectively. Before that, it was such a long and tedious procedure that it was just an interesting theoretical curiosity. But in the beginning, I never had data, I never had friends. I was a theory, wafting around, waiting for a place to happen. And my personal computer, which was a 286, could only do 1,000 numbers at a time, and I kept having to save the formulas as values and get rid of everything that I didn't. So even 1,000 numbers in 1989 was a very daunting task. So I thank, each morning I thank Intel and I thank Microsoft for actually taking the personal computer and in 10 years making it cost efficient. Had I discovered Benford's Law in 1979 with no computing, with no personal computer, it would have been very lonely, and I would have been very disgruntled because nobody would be using it, because it would have been so difficult to use it in any respect. So I think I got it right at the right time. So, as I say, I was a theory wafting around waiting for a place to happen. And in the beginning, I would read the published papers on Benford's Law, and the published papers were generally mathematical papers, and what they did, they would do interesting things like the Fibonacci or Fibonacci sequence. If you remember that, it's the sequence 1, 1, and then we add the previous two numbers. So we go 1, 1, 2, 3, 5, 8. And so we'd get that Fibonacci sequence. And what the mathematicians found was that Benford's Law applied perfectly to the Fibonacci sequence. In fact, the first 100 numbers give a very good fit, an exceptionally good fit for 100 numbers. And if you went up to 400 or 500 numbers, it would look absolutely splendid. It would be a really nice graph. So what we have, and so these were my thoughts in the beginning, we have the Fibonacci sequence applying to many natural phenomena, and the mathematicians would show how it would apply to rabbits and things like that. And we have Benford claiming that Benford's Law applies to natural phenomena, and so this actually started to make sense. Fibonacci sequence applies to natural phenomena, Benford's Law applies to natural phenomena. The Fibonacci sequence follows Benford's Law. So I'd lots to keep me busy with in the beginning, but I never had data or friends.
Well, now you have 40 friends. But, I mean, so there's some condition, I guess some growth condition on a distribution that gives you Benford's Law, like any recurrence then within.
Either growth or, it was in the American Journal of Physics in '85, where somebody showed that all we really need is a phenomenon where there are more small things than large things. And he said very logically, there are more small lakes in the world than large lakes. That's why we call the big ones the Great Lakes. And so when you have many more small islands than large islands, more small rivers than large rivers, more small towns than large towns, more small companies than large companies, when you have more small things than large things, the natural result is for Benford's Law to come out from the set of data. So it doesn't actually have to be growing like lakes. It could just be, it must be something where there are more small items than large items, which helps. So let's do a little bit of data here. So in the beginning, no data, no friends. Here it is. So So my only source of data would be data from public records. And so this was one of the very first data sets, and this was census numbers from the 1990 census. And what we have on the left, we have the county number, and that's just a reference for the Office of Demographics. Then we have the county name, and I ask you what state I'm in. California. And the first column of numbers is the population for the county according to the 1990 census. The next two columns are projections for 91 and 92. And so in the beginning I thought this was a list of 3,141 counties. I thought it's a really big list of numbers. Wow. Let's see whether it works. And now, when I go out to the airlines, we're often faced with data sets of 100 million observations, which is very big. It's bigger than 3,000. Would you think this set of data would follow Benford's law? Sure. I was hoping so. And then, da-da-da-da, here we go, and to thunderous applause. I'm actually waiting to do this at Carnegie Hall next year. And so what I'd like is to tell them the story about Benford's law, and then I want blue smoke coming out from the back, and a lady on a Harley Davidson to rip by, and as the smoke clears, the graph should come out from the background. And so then we should see Benford's law to thunderous applause. It's just a dream.
Everyone needs a dream.
We all have a dream. It's been a long, the first 6 years were very lonely. The center line is Benford's law.
We could have done it.
Thank you. The dark center line is Benford's law, 30.1, 17.6, 12.5. The bars show my actual proportions, and so for the 6, when the actual proportion is right where the diamond stud is, it means my actual and my expected proportions are equal. Now, this is 3,141 numbers. I tell you, hear me today, this is a very good fit. And it's not often that we get a very good fit with 3,000 numbers. And for my final crescendo, and if you can organize it in about 20 minutes, we'll go for the final one. I'll show you the Florida election results. Because what I have is I have census numbers from counties, and the census numbers are counting people. What is an election? An election is simply taking all the people in the county and breaking them up essentially into 3 groups. Voted for Bush, voted for Gore, didn't vote at all. So if I take each number for the population numbers for the county, and I essentially break it into 3 groups, those 3 groups, I think, should follow Benford's law. The source data follows Benford's law. So yes, I have upper and lower bounds, and this gives me more problems than most. The upper and lower bounds are based on something which I would call the Z statistic, the Z statistic, and it's based on the 1.96 or the 2.57. Where it gives me problems in auditing is I keep telling them that the statisticians have done a really nice job, and we have the concept of significance, and when we go over, it's significantly different, and when we're under, it's significantly different. But auditors don't care about significance. They use words like materiality, a material difference, and they use words like tolerable error. This is auditing jargon. And a material difference and a significant difference are not the same thing. So I have big problems in auditing when I put those bounds in, because the auditors want something to bite onto, but the concept of significance and the concept of a material difference are not the same thing. But your question, the answer to the question is yes, those are significance bounds. I just used the Z statistic and set the cutoffs. The problem happens when the data sets get very big, the level of error shrinks So that in the end, conceivably, if my data set is 5 million observations, you won't see a difference between the three lines. They would just collapse onto each other. So those are the first digits.
What kind of goodness of fit test are you using?
And this gives me a problem. The question was, these are the second digits. What type of goodness of fit test do I use? And what I need to do is I need to develop tests so that they are independent of the size of the data set, because the moment size comes into play, these bounds keep shrinking. And the one that I use for auditors is the mean absolute deviation. And so if we just go back to basics, deviation is the difference. Benford, actual, deviation. I talk to the blackboard. Teaching 101, do not talk to board, talk to audience. I have the deviation, the absolute deviation means that I don't care which direction it is, I just use the positive amount, and the mean absolute deviation is where I just take the average of all my deviations. For second digits there would be 10 deviations, and I would take the average. And so I have metrics based on the mean absolute deviation. And the guidelines that I give auditors are those deviations that I've seen from data sets where I expected it to fully comply with Benford's law, then I test, and then I still get a deviation, and those are the guidelines that I use for auditors. Well, the theoretical one is Benford's law. That's the expected. And this is it. This is the 12% going down to 8.5. At least that's my expected distribution.
I wonder if you're talking about the distribution of your test statistic here.
Oh, okay. And I haven't done all that much work. I have my mean absolute deviation. I have certain cutoff levels, which says if it's higher than this, that data set doesn't look that good. But I would welcome more work in the field. We really need it.
What about, say, like Kolmogorov, Smirnov?
And I have used Kolmogorov, Smirnov, and from time to time I think that when I think of Kolmogorov, Smirnov, I think that to be a good statistician you have to drink so much vodka that they actually name the brand after you. But Kolmogorov, Smirnov does work well. And from time to time I do use it. Census, New York Stock Exchange. My favorite issue of the Wall Street Journal is the one that comes out on the 2nd of January each year, because it's got the year in review. It's got all the numbers from the preceding year. Actually, now that I think about it, that's my second favorite issue of the Wall Street Journal. My favorite issue is one that I was in. But the second favorite issue is the year in review, and I generally analyze something out of that year in review. And from time to time I will look at the volume numbers. Each company has got a volume for the day. There are about 250 trading days for the year, and so we take all those trading volumes for Procter & Gamble for 250 days, they add them up and they give you a volume for the year. Yesterday was quite significant. We had two companies on the NASDAQ each go over 100 million for the day. So these volumes for the year can get very big. And so I ask you whether you think these volumes would follow Benford's law, bearing in mind that there are about 3,000 companies listed on the New York Stock Exchange. To thunderous applause, it's very old Excel version 4 or something. That is a very, very neat fit. And not only is it a very neat fit for 3,000 items, but the companies on the New York Stock Exchange are not a random sample of companies. You're on the New York Stock Exchange when you are the biggest of the big. With a few exceptions, the NASDAQ has got some big companies listed. But I would say generally the New York Stock Exchange is the biggest 3,000 companies in the United States. And for the biggest 3,000 to follow Benford's law is quite amazing. I think so. Just a little quote from academia here. This paper was published by Ralph Ramey in 1976, and this was a chronological review of everything that had happened up to 1976. And he says, the particular logarithmic distribution of first digits, while not universal, is so common and yet so surprising at first glance that it has given rise to a varied literature, among the authors of which are mathematicians, statisticians, economists, engineers, physicists, and amateurs. And you will notice missing from that list are accountants. So it is only in the past few years that I've worked very hard to get accountants to start using this, because my thought was, let's use these digit distributions to help auditors figure out whether a set of data appears to be authentic or whether we have some abnormal duplications in the list that could help point auditors to areas that might warrant further investigation. I have a few fraudulent data sets, and I won't go through those graphs, but generally what we're looking for is cases where people are actively inventing numbers. And one of my examples was a shop owner that invented the daily sales numbers out of her head. And so what we see in the pattern of those graphs are duplications in the digits, because even though people are trying to be random, we really don't succeed at being random as human beings, even if we try. One of my more interesting data sets was President Bill Clinton's tax returns. Oh, I can still say President Clinton for another month. And this is May of 1994, and of course Benford's Law was part of my life. It was my PhD dissertation, so it was my life for well over a year. And people were investigating his tax returns, and so people were Money Magazine and One Tax Journal and all the reporters and everybody were questioning his tax returns, at which stage I said to myself, I said, I have to see this man's digits. And so for a modest fee of $174, and 2 weeks later, I got 16 years of tax returns delivered to St. Mary's University in Halifax, Nova Scotia. It was a daunting box, but it was the actual returns with the covering letters and everything for 16 years, 1977 through to 1992. It had all the social security numbers and Chelsea's number and signatures and the cover letters. It was the complete package.
Anybody could request that?
If you run for office, you have to submit it, and anybody can request it. So, which is why Howard Stern would not run for governor of New York, because, well, he claims, because you had to submit your tax returns for the past so many years, and he was just not going to do that. At least that's what he said. So I got it, and together with a tax professor, we hold out those numbers that could be manipulated. And on a tax return, not every number can be manipulated. For example, subtotals. The IRS believes, it's on videotape, the IRS believes that whenever you have three numbers remotely close to each other on a page, you need to subtotal before you can carry on with the rest of your life. And so I would leave off things like subtotals or numbers carried forward from other pages or numbers where you have to go look something up on a table or those type of numbers. And in the end, I had about 300 income items. Income items we defined as numbers. The bigger they are, the more you pay. 300 income items. I gave a talk in Houston. It was a lunchtime talk. They had about 4 minutes on the theory of Benford's Law. Then I told them about Bill Clinton's tax returns, and I said, do you expect these tax returns to follow Benford's Law, yes or no? And I heard a resounding whoa. Then I realized I was in Houston, and they'd only heard about a theory for exactly 4 minutes, and they believed that the president must be breaking it. Very nice fit. Very, very nice fit for 300 items. Bear in mind that this is from 1977 through to 1992, which gives us a nice spread of the numbers. If I took any particular year, such as next year when Mrs. Clinton gets the $8 million advance for her forthcoming book, we'll have the numbers will be clustered in a certain area of the number line. But spread them over 16 years, and it's a very good fit. Extra first digit ones, extra first digit sevens. At that stage, their speaking fees were $1,000 or $750. So we go back, we see lots of thousands, lots of 750s, and this is my explanation as to why it happens. A new phenomenon has appeared on the web. A program was developed in Turkey, the country Turkey. And if you go to the website Benford Wiz, W-I-Z at the end, you will see that this software is being offered as anti-Benford software. In other words, he's giving you software that will form a set of numbers that follows Benford's law, so that if the auditors want a list of numbers, you've got a list of numbers that follow Benford's law. The selling price is $514, which I think there are 190,000 Turkish things to the American dollar. So $514 is an awful lot of Turkish things. Benford Wiz will give you a set of numbers following Benford's law. His problem is twofold. He doesn't realize that if an auditor only takes the data and subjects it to Benford's law and walks away, that's too little. I want this to be the start of the process, not the process. Number two, he doesn't realize that in each data set that I see, I always see bumps and hiccups. I always see some spike somewhere with an explanation. The spike is at different places and the explanations are different, but I never see, well, I seldom see something looking like that New York Stock Exchange of 1995. It is never so neat in real life. These are the income items, 300 of them. Well, on a tax return, we also have deduction items. The bigger they are, the less you pay. 600 items, 500. Benford's law, to thunderous applause. A very nice fit. It was 1996. I was in Halifax, Nova Scotia, and they had the G7 summit there. I knew which hotel was President Clinton's hotel, because when he stays in a hotel, that's what happens. He stays in a hotel. At 6 o'clock on a Saturday morning, I took my paper down there, and I told the Secret Service that I had a package for President Clinton. Let me warn you that that is not a very clever sentence to say. We can just leave it at that. Just a few more things, and then we'll wrap up. I was giving a talk in Albany, New York, and I knew that Schenectady was just down the way, and there would have been Benford's old house. So I got into my car, and I drove down to Schenectady. And I knocked on the door, and I said, you know, a famous person lived here. Could I have a look at your house? And he looked at me as if I was some kind of a nut. But I was getting used to those looks, so they didn't bother me that much. In the end, he let me look at his house. So that was Benford's house, and the study was on the second floor in the back left. And so I spent quite a lot of time just kind of getting the vibe in the study. Just kind of staying there. I have two more, so I'm glad you asked. And so then I stayed as long as he would let me before I realized that I was going to be asked to leave. And so there we go. We can't pass up a good number without going past it. And of course, there's the dog in the back probably saying, let me just bite that nut. Get him out of here. The point I do want to make to those of you that might just be starting off and just looking for something to latch on to, you have to be immersed in the topic. I mean, you have to like it so much that you go to the house and take photos and do all those extra things. If you like it that much, then it stops being work. Some studies that I'm busy with at the moment. The Civil War, I was on eBay, and there was a book called Numbers and Losses from the Civil War in America, 1861 to 1865. I said, hallelujah, a book printed in the year 1900 with only numbers. What could be nicer? And so I went through the book, had to read the whole book and enter all the numbers manually. And so what we had were about 1,300 numbers in the end, from battalions and people killed and wounded and missing. Really fun stuff. Numbers that went into battle. And these were all from the Civil War, and the book was published in 1900, so I have a 100-year-old book, and I wanted to know whether Benford's law applied to it. Maybe I could draw the amazing conclusion that war is a natural act, or war is an unnatural act, based on the digits. First digits, troops in battle, killed, wounded, missing, battalion counts, and so forth. That data set, unfortunately, is right on the border of what I call conform or not conform. It's right there. It's at the cutoff level. So I can go either way with that decision. And these studies are the hardest. It's the hardest when the data set is right on the limit. So I don't know which way to go, and I'm not exactly sure why. So those are the first digits. If we look at the second digits, which is the second slide. There it is. Lots of extra zeros, lots of extra fives, telling me that there's lots of estimation in the data set, and estimation is reasonably natural. I would think this is a civil war. Accounting is not the highest priority. So we do have to estimate at times. And also from what I could see, some battles followed very shortly after another battle. If you got attacked on Friday, and things didn't quite settle out on Friday, you can have another battle on Sunday when the opposition brings in more troops, and you'll have a new battle. So there's no real time to count the leftover troops on Saturday. It's a matter of, we have a war at hand. So I see that. And so if anybody has any suggestions, whether any history journal might be interested in considering publishing something like this, whereby all we say is this is perhaps a methodology that we can use to test archival data to see whether it has some semblance of reasonableness. And all we simply do is look at the patterns of the digits to try and draw some conclusion as to whether the numbers at first glance appear to be reasonable or not reasonable. Back to the presidential counts. These are the Florida results. About 700 numbers. And these are the people that voted for president, actually the ones that could actually do the little, that's very hard, pushing the Chad through. So these are the people that successfully did the Chad trick and got their vote counted. Benford or not? To be Benford or not to be Benford? Again, it's right on the border. It's not a very good fit. It's right at the limit of whether I think it's a good fit or not. And so,
these are the proportion of what?
These are the actual numbers for people that voted for president. So for each of the 67 counties, I have about 10 numbers. This would be the number of people voting for Bush, number of people voting for Gore, Buchanan, and so there were about 10 candidates on the ballot in Florida. So for each of the 67 counties, I have about 10 numbers, giving me, say, 670 in total. So these are the actual vote numbers. Even they would be surprised that they do have lots of first-digit ones. Second digits. Very messy. Very messy. Very messy. I also like to look at the last two digits. And for the last two digits, I assume that the last two digits should be evenly distributed. Because if you look at Benford's law, you'll see as we go to the third, fourth, and fifth, it smooths out. So it's a reasonable assumption that the last two, it's a simplifying assumption, should be evenly distributed too. And here I do get a little bit of a surprise. That's the complete set of election counts. Well, we'll just have to live with it. Those are all the elections. So they also voted for Senate and House and Chief Dog Catcher and Fort Lauderdale and so forth. And so I have 1% of all numbers. That's my expected for 00 through to 99. And what does amaze me here is that I'm a little bit short. I'm short in numbers that end in 00. And I'm over in numbers that end in 99. And what numbers that end in 00 sound like estimates. And when we're doing election counts, the last thing we wanted in mid-November was for our numbers to look like estimates. So I am just a little bit amused, and only a digit graph amuses me. I'm a little bit amused that we actually are short on numbers that end in 00, and we're over on numbers that end in 99. So I'm always wondering whether the Political Science Journal might not be interested in this, and I was talking to somebody here yesterday. The long and the short of it is I'd be happy to do such a study with anybody here. However, I'm not that interested in the county numbers, even though that's what I'm showing you here. I'm more interested in the precinct numbers, because the county numbers are simply the precinct numbers added together. And what I want to do is I want to get back to those source numbers, the precinct numbers, because they are what you might call the source data, and I would want to analyze that to see whether we have any digit patterns that look or don't look troublesome. The county numbers are simply the totals of the precinct. The precinct numbers, would I expect it to conform to Benford's law? Maybe not, because the precincts might be so close in size, because that's how we sort of work out how big the precinct should be, that if, say, the average size was 3,000 people per precinct, then I'm going to get lots of numbers that are around 3,000 numbers, and so the precinct numbers might not actually have the spread. The other point that I want to make about the election results that might disturb the first digit graph, because the election results were so close, if Bush got 82,000 votes, then Gore probably also got 82,000 votes. So the first digits for each candidate would be equal, because it was so close. I'm sure that at the first digit stage, they would have the same first digit for each county. The differences would only start coming about on the third digit or thereabouts. And so this sort of doubling up, because the election was so close, this doubling up might cause my graph to have some bumps and hiccups. Just a story about auditing. When it comes to auditing, what I do here is we start off with Benford's law, and I go into patterns such as the first two digits and so forth. And what Benford's law gives us, it gives us a nice starting point. And I would use these graphs trying to look for abnormal duplications. For example, this was one study that I did in California. And here it is. This is the last slide. I did a graph of the first two digits, and this was company disbursement data. This was about $500 million, about 200,000 invoices. I do the first two digits, and amazingly, for the first two digits, the 10 has an expected percentage of 4.1. The 99 has an expected percentage of about 0.5. the 10 is about 8 times as likely as the 99. This is authentic data, California, July. I see that I have in my payables data excesses at 1011, 50, 9899. And from an auditing point of view, we then start running more and more tests to try and dig up what is causing the disturbances in the digits. So it's a starting point. It's not all we do. If you think that buying Benford Whiz would actually work, your graph will look too neat to be true. So that's the story. I'd be very happy to field a few questions, and then we can have our tea.
Did you find fraud as the cause of those?
No, when we went to the actual numbers and looked for actual number duplication, what we do find is that this company actually had 6,000 numbers of $50 in its disbursements. And again, what this tells me is that something is happening that is very repetitive in the data, and it might or might not be the fraud. It could be a processing inefficiency whereby we just do the same thing over and over very inefficiently.
I guess you can take a look at election data from places and times where you have a corrupt administration in Chicago.
Yes, no, and actually I think this would be very nice. And we're talking about corrupted election data whereby we know it's corrupted. And again, I would want to get down to the source data. I don't want a county total. If it's done by precinct, I want precinct by precinct numbers because that's where the fraud is. So I would be very interested in doing it. I have a year off, so this is my life. And by the way, if you haven't done all your Christmas shopping by now, then this really would go down very well. I'll just.
Can you give a couple of examples of where you did detect fraud?
Yes. In fact, at one bank, we ran this test against credit card amounts written off as uncollectible. So somebody in the bank says, we're not going to collect, and they do a journal entry. And we ran the first 2 digits. We found a huge spike in excess at 49. And we went into the actual numbers, and we found lots of amounts being written off between $4,900 and $5,000. And it turned out that one manager had as his limit $5,000. He was having cards issued to friends and family. They would run the balance up to $4,900 and something. He would write it off as uncollectible. Next card, next friend. And because he was systematic, and he was greedy, and he went to his limit, we picked it up in the digits as an abnormal duplication.
Do you think anybody in this audience would be smart enough to write a Benford program which you wouldn't be able to detect? In other words, it wasn't too good. It wasn't too close to fit.
I think you could do it. In this audience, you could do it.
We could charge less.
And you could charge less than $514,000. You could do it.
Does that worry you?
This worries me now. So I'm going to be worried now for Benford Whiz version 2, PlayStation 2.
How do you make a judgment that you expect to have variations? Of course, that's what you're saying. That's how you detect. So how do you determine when it's too much, too many bumps, and you start to look? Is this a really sort of a by-eye, gut feel kind of thing? Or?
It's a little more than that, because in auditing we do have some standards to guide us. And so, for example, if you look at this company, the number of $50 appeared 6,000 times. It caused that huge spike, but in dollar terms, it's immaterial. You see, if you multiply 6,000 by 50, you get 300,000. The data set was 500 million. So I might even just look at that spike and say 300,000, 500 million, it's immaterial, I'll pass. But this does require practice. Because I would think a novice would say that spike was so big I have to look at it.
Well, I guess what I'm asking is how big is it beyond where you would even sort of notice it? I mean, how do you make a determination as to whether it's more than just one of those random bumps that you actually expect. It sounds like that's just sort of an experience by eye kind of thing.
It's experience by eye, and I would say I've done at least 70 or 80 data sets in depth where I really take them seriously, and so it's practice.
Have you tried working backwards to look at the sensitivity of your technique of finding data sets that are known to be fraud, say, for companies?
Yes.
And seeing what the probability of your finding it is?
Yeah, and this is what I did in the beginning. I would actually go to court records, and where the person was actually convicted of was convicted of fraud, and so I would then work backwards and look at those numbers. This was one of the first ones that I published. And so from fraudulent records, at least from fraud numbers from court records, I would work backwards, and then from the known fraud, see whether it follows Benford's law. And we've had a number of cases where companies have gone, and now that they find the fraud, they run it against Benford's law, and then they can actually see that it departs. A recent case was where a controller of a division of a company said to his assistant, well, he didn't actually say this, but he was too important to approve for payment the invoices under $5,000, and he was going to delegate this responsibility to her. It turned out $500,000 later that all the numbers that she approved were for $4,300 and something and $4,700 and something. She kept the numbers in those range, and again this suggests to me that she somehow wanted to tag her numbers so that she knew which numbers were hers, so that if anybody phones and she'll ask the dollar amount, you would intuitively know, now it's one of my numbers or it's not. And so we've seen these cases many times. People do repeat their actions. And often they come in just below what we call approval limits or just below control thresholds. And the most favorite number that I see in corporate expense accounts is $24.50, because people have this requirement that we only need a voucher for $25 and higher. And so everybody goes to $24.50. And this amazes me that a person can be working at a company with 18,000 employees, and they think they are the only ones to have figured out this thing. I'm the only one to have thought this out. And so the favorite number there is $24.50.
Speakers, please pick up a...
That's right.
If we have an expense, you have to be very good with making up the numbers.
By Benford with numbers. All right, any more questions?
I have a few copies of my published papers up front here, and I'd be happy to look. The papers are free.
You heard about your experience with income tax in other countries? Or you have applied this to income tax?
Yes. And actually, some of the studies that we did were, that we have these forms 1099, whereby the banks send you a form saying how much interest. And in Holland, what we did was, it was a very simple study. We took a whole sample of 1099s, and the numbers on the 1099s for interest followed Benford's law absolutely perfectly. We took those same 20,000 taxpayers, and we ran their interest received numbers through the simulation, and Benford's law was not to be found anywhere in the data set. And the bottom line there is that the Dutch revenue authorities didn't do an automatic check. The 1099 just arrived, and if somebody did happen to look it up, they could, but it wasn't automatically checked by the computer. So here we have a case whereby the bank that has no incentive to defraud, that data followed Benford's law very nicely, whereas the taxpayer data was, Benford was not to be found in Holland.
Okay, well, thank you very much.